Hello, everyone, and welcome to our seventh Air Quality Forum. My name is Johanna Angeline, and I will be your moderator for today. I believe it's going to be an interesting and excellent discussions because we're now having two excellent guest speakers. But before we start, I wanted to make sure that all of you know here that we're committed to a respectful learning environment. So please find a brief of conduct in the chat box. Before we jump, I wanted to do a bit introductions. Our first speaker here is Dr. Karoline Barkjohn. She's a physical scientist at the U.S. Environmental Protection Agency, EPA, and today she will present on the United States-wide sensor correction. Dr. Barkjohn is part of the EPA's Office of Research and Development Center for Environmental Measurement and Monitoring, where she focuses on understanding and improving the performance of air sensors. I think without further ado, I can just invite Dr. Karoline Barkjohn. Dr. Karoline, the stage is yours.
So today I want to talk about US-wide correction for air sensors. I'm going to start off with some background, talk through the correction development and improvement. We've kind of improved the correction over time as we've learned more. And then I'll touch briefly on some limitations of the Plantower PMS 5003 and then touch on some resources. And I wanted to start off with kind of a quick definition of what I think is the difference between air sensors and air monitors, right? So air sensors, they're typically less costly with more simplified measurement conditioning methods. They're more portable, and typically they're going to use less skill for basic operation, whereas, air monitors are typically the more accurate measurements. In the U.S., they include things like the federal reference and federal equivalent methods that we use for regulatory measurements. And so they're more established approaches. And so a lot of my talk is really focused on making air sensor data look more like air monitor data. So I want to start with just a little motivation for our work. As many of y'all probably know, air sensors can really provide more spatially resolved air quality information. So here's an example from the fire and smoke map. Where you can see a part of Colorado with just a couple of air monitors. Even though we have a lot of regulatory monitors in the US, there's still places where it would be good to get more data, especially in areas with mountains or sources where the concentrations can change very quickly. So here you can see with additional sensors, filling in additional gaps on the bottom map there. And so most PM 2.5 sensors are not accurate out of the box. And so correction is typically needed. So here's just my very basic diagram. You see the dashed lines, we have sensors, and then, we can adjust them so that the measurements look more like the monitor measurements. So your sensor may show the same trend, but it may read 2 times higher. And so we can adjust for that so that the measurement is in a meaningful unit. And for this work, we used purple air sensors. These were really widely used and available, and they were being reported by the public and media outlets. This work started in 2018, and so this is one of the sensors that was really popular and one of the first ones to really gain a lot of popularity. And obviously, there's a lot more sensors in the market now, 6 years later, but this is one of the first ones, and so that's why we focused on it. It was also being evaluated by U.S. air monitoring agencies. And one note is that, the Plantower sensors are also used by other sensor manufacturers. So whether it's this PMS 5003 or other versions of the Plantower, this is a very popular sensor for measuring PM 2.5. And so this is a little bit detailed of a slide, but it's really important to some of the things I'm going to talk about. Basically, the Plantower gives you 2 different estimates of PM 2.5. And so it calls them correction factors, CF1 and CFATM. And so you can see this plot here where basically they have a 1-to-1 relationship at low concentrations, but then at higher concentrations, the CF1 reads higher by about 1.5 times. And so what we've found is that the CF1 is more strongly correlated with our federal reference method and federal equivalent method in temporary smoke monitors, so all these kind of conventional methods. But the CFATM we use, for example, on the fire and smoke map because Purple Air gives us that real-time 10-minute averages, which allows us to do faster computation. So It's a little bit detailed, but it's just important to always keep in mind, which estimate you're using from a sensor to make sure that the results are reproducible and that you're getting what you expect. So just a quick introduction on correction equations. Our objective is to use purple air data to estimate the correct air quality index category. And so those are categories you can see at the bottom there, from good to hazardous, and there's different, health protective advice in these different categories. And so we want to develop a correction that reduces the error in each of these categories. So we want the data to be accurate in telling you, is the air quality good or moderate? And then we also want it to be accurate all the way up into telling you, is the air quality hazardous outside, the PM 2.5. And so we compared purple air sensors operated alongside air monitors at government monitoring sites. Okay, so moving into the correction development and the movement and the improvement over time. So we developed and tested our original correction on 24-hour average data from federal reference and equivalent methods in 16 states across 39 sites. And so we had 50 sensors, and we had about 33 years worth of data. So not quite a year on average per sensor. Some sensors ran for shorter, some sensors ran for 2 years, but just a lot of data from all over the country. Obviously, it's going to be very hard to ever capture every single kind of local situation and sources, but we have captured a lot of it. And so we considered a whole bunch of different equation forms in order to correct this data. So, everything from a really basic linear fit, and we also considered different parameters that could impact sensor performance. So relative humidity, temperature, and dew point, and kind of all the different combinations of those terms, getting into more and more complex equations. And so this is the equation that we selected. You see there's a slope term times the purple air output minus a term times the relative humidity as measured by the sensor, and then an intercept. And so we did consider these more complex corrections, but they didn't really improve the performance significantly. And we tested this based on fitting a correction to all but one state and then testing it in the state where it was not trained. So for example, we developed a model for every state except for Florida, and then we would test it in Florida, and we would do that for every state to see, how well this correction is likely to fit in other parts of the country where we didn't have any data. So why is the relative humidity correction needed? So most the monitors, the regulatory monitors in the US, measure PM under controlled humidity. So sensors, they don't dry the PM or control relative humidity. And so water can cause the particles to grow, potentially scattering more light and leading to higher estimates of PM 2.5. And real briefly, I want to touch on the quality control. So purple air has 2 of these internal planetary PMS 5003 sensors. And so we're able to throw out measurements if they disagree, right? So if only one sensor reads high, it could be a sensor problem, whether that's a bug that's living in there, some kind of electronics failure. But if both sensors read high, the PM 2.5 is likely high. And that could be something, that sensor may look way different than other sites because maybe someone is smoking right under your sensor, something like that. But that's one level of QA we can use. So I already touched on the CF1 and CF-ATM, and so this was something that we originally had wrong. We had developed the equation for CF1, but only the CF-ATM data was available pre-averaged from purple air, and so initially this correction was applied to the wrong, basically the wrong column of data, resulting in about a 33% lower concentration when the PM 2.5 was above 25 micrograms. And so we just created a version of the original equation to kind of correct for that difference where the CF-ATM data was lower at higher concentrations. So you have a piece where it's less than 50, here's the equation, and when it's greater than 50, here's the other equation. And so then we continued evaluating this correction, and we saw some extreme smoke. And so you see here, the monitor is reading up to 1,500 micrograms per meter cubed. So this is during some of the major wildfire smoke events, primarily in the western United States. And so we see this strong underestimation from the sensors above about 300 micrograms. And so we ended up pulling data from 25 different US cities to update the correction. We used hourly data instead of the 24-hour average data that we had used originally. We used nearby, so sensors and monitor pairs that were picked off of a map, or these true collocations that were run by typically government agencies. And we used both extreme smoke and typical ambient conditions so that we would get this performance, strong performance across the full range of concentrations that we would expect to see. And so this plot just shows you on the top here, multiple sites hitting 500 micrograms per meter cubed. So very high concentrations, kind of a range of relative humidity, and kind of a range of dates, some just short deployments and some longer term. And so here's the next equation that corrects for this nonlinearity at high concentration. And so what you see is a purple layer square term that has been added to account for that nonlinearity at high concentration. Again, we consider multiple equation forms. You'll notice that the top piece does not have a relative humidity correction. And that's just because we had so much less data at high concentration that it was really hard to understand what the RH influence might be, the relative humidity influence might be at those really high concentrations. And so lastly, we got some emails when this correction was in use on the map where people were seeing some kind of strange behavior where the concentration would change just slightly. And if you were near the breakpoint between these equations, you would end up with a jump. And so you can kind of see some gaps here with this three-piece equation. And so we ended up adding 2 transition zones. And so I know that this looks like a very complicated equation, and it is, but I'm trying to walk you through kind of how we ended up with the 3 pieces to correct for the nonlinearity, and then these 2 transition zones, just so that when you don't get as fast of a shift. And so this is what it looks like over kind of a wide range of concentrations. You see kind of the 2 lines where the lower line is 100% humidity, and then the higher line is 0% humidity. And so you have the low concentration, then you have a transition, the mid equation, and then another transition into that quadratic equation. And so this keeps the error within about 20% at each air quality index breakpoint as compared to the monitors. And so we have a paper published on this equation that uses the CF1 data. So it's a little bit different than what we're using on the map. And so if you want to learn more, you can read that, and I'll have a link later. And we're really hopeful that this method that we've used could be used by other sensor manufacturers or data analysts in order to improve the accuracy of sensor data over the full range of the AQI. And so this is based on the old AQI. The PM2.5 AQI was just updated in the United States, but basically we looked at kind of right around each breakpoint, right? So the breakpoint between good and moderate was 12. So we looked at the data between 10 and 14, plus or minus 20%. And we saw a bias of negative 10%. And so we were trying to keep the bias within each of these bins at, less than equal to 10%. And so you can see we achieved that. We also have this Cal OSHA. This is the California occupational standard for wearing a respirator. So, you could do similar analysis even with different breakpoints of interest wherever it's important to make decisions for your work. So lastly, just touching on the limitations of the plant tower. So there's a lot of work looking into kind of the performance of the purple air and the internal plant tower sensors and kind of what size of particles that they detect. So the sensors are measuring light that's scattering off the particles. In larger dust particles, they can scatter much less light per mass. And so sensors end up underestimating compared to the reference monitors during dust impacts. And so you miss some of these larger particles. And there's also a manufacturing deviation where there are some newer plant tower sensors that read slightly lower concentrations than the older plant towers. And so they look the same on the outside, but they have kind of different readings. And there is a way to identify them if you look at some of the size bin data. So lastly, just some resources. I can provide these links and we can share the slides after. If you want to learn more about EPA's work with air sensors, you can go to the Air Sensor Toolbox. Two resources you might be interested in are the Air Sensor Performance Targets and the Enhanced Air Sensor Guidebook. Also in March, we're hosting an air sensor workshop. It'll be here in Research Triangle Park, North Carolina, where I'm based, but it'll also be virtual. Attendance is free, and we're also accepting abstracts. If anybody has any work they'd like to present on, those will be due November 1st, so in about a week. I'd like to thank all my coworkers and all of our collaborators who this work would not have been possible without them. And with that, I'm happy to take any questions and feel free to reach out to me by email if there's anything we don't get to address today.
Thank you so much, Karoline. I think it's time for questions. We have 5 minutes for a Q&A session. So if anyone wanted to ask questions regarding the materials, feel free. You can leave it on the chat or might as well ask this in live.
Maybe I can break the ice here, Karoline. Thank you for the presentation. We have recently, actually we're just starting an experiment right now because we still see differences in batches from plant towers, maybe around 2, 3, 4 micrograms between just basically from last year as well. So I was wondering if that also came across you so far or not. I mean, it's something we currently look into, so I was just wondering if that's something that came up.
Yeah, so I think that my understanding is that those kind of different plant towers have become more common over time. And so I don't think it was really impacted our initial analysis that was kind of in 2019, 2020. But it is something we've kind of kept an eye on. And I think that the kind of takeaway for us is that even corrected, if you're using the PM 2.5 data, the difference is about 1 micrometer or microgram per meter cube. So it shouldn't be that large overall.
Good.
Okay, we also have questions from Olhad Zifan in the chat box. So if I may read the whole thing, it's quite long. PM 2.5 is historically used for air quality after the Oxford 6CT study. You showed the RH corrections, but human lungs have different RH from the environment. Medical doctors consider RH to be 100%. Recent study found 50 to 90% across multiple people, and there's also a link attached. The question is, why not support an epidemiology study to start the transitions to particle counts and not under the mentioned? And then there's also another questions here, but maybe we can start with the first questions first.
Yeah, so it's a good question about considering particle counts instead of mass. And I think that so far, a lot of the particle count measurements are still a little bit more complicated to do accurately and more expensive. And so I think maybe over time, as the measurements become easier to make, there'll be more and more data, which will, I think it's kind of a chicken and egg situation where the more data you get, the more you can look into the epidemiological effects. And also the more effects that are shown, then, you know, the more likely people are to invest in these measurements.
Okay, I hope that answered the first question. And then another question is, what is the lifetime for these sensors? Those I've worked with were valid for 2 years, officially anyway.
Yeah, so for the PM sensors, I think there's been some work that shows a lot of them will last for 3, 4, maybe more years. A lot of these sensors really have only been out for 5 years. And so the number of them that are really that old is not that many. And I think, some of them do get catastrophic failures where the fan stops working, where you get crazy values. And those are kind of can kind of come at random anytime from a quick failure to longer failures. So it's a little bit dependent, but it seems like there isn't that much drift in order to invalidate them after a couple of years. So hopefully they'll last longer.
Thank you, Caroline. There's also a next question from Lauren. It is done a lot nowadays. Did you already consider to use the color theory to compensate the particular growth due to high humidity?
Yeah, so we did consider some of the more complicated nonlinear relative humidity corrections for the data, and we didn't see that it was needed. And I think that there's a couple reasons for that. First of all, in the US, a lot of our sulfate emissions have really reduced in the past, 10 years, something like that. And so some of the types of PM that really grow exponentially aren't as prevalent. So I don't think they're growing for that reason. And potentially also there's something about the way the sensor is designed. Maybe it's a little bit warmer in there, or maybe once the particles grow, they just aren't really detected by the sensors accurately. So we did consider it, but it wasn't needed in the US, but it could be needed in other parts of the world where you have particles that really grow more with humidity.
Okay, moving on to next question from Nasser Khan, joining from Eastern Saudi Arabia. What will be the impact of these corrections on both consumer or industrial devices? How will this be communicated, assuming it becomes standardized?
Yeah, so that's a good question. And I think basically the idea is that if you looked at this data uncorrected, it would give you really strong information in terms of trends, right? So the R squared is high. So when you see upward patterns and, higher AQI colors or whatever, it would be more likely to need to take action to protect your health, right? So, those kind of actions. But I think that by correcting it, we make it look a little bit more like the regulatory monitor data that people are more used to seeing. And so with that correction, we can show the sensor data side by side with the air monitors. We don't necessarily have the same confidence, we have less confidence in it, but without a correction, the sensors would often be reading different categories than the other monitors. So this is really a method to be able to tell a similar story with our conventional air monitors and the sensors. So I hope that kind of gets to your question.
Another question from Saverio. Did you notice any substantial drift?
Yeah, so not in this work. There's some other more recent work that has shown maybe like a 1 microgram drift over 4 years or something like that, but pretty minimal.
Next question is from Ailish Graham. You mentioned there is no RH term included in the correction at high concentrations, such as those seen during wildfires. Would this limit the correction used in other regions of the world where RH is very high, for example, in tropics?
Yeah, so that's a good question. And I think that that's really going to depend on what is the composition of that really, because this is really only about when the relative humidity is really high and the PM is also really high, right? Like 3 to 1,000 micrograms per meter cube. So may matter kind of what are those particles, but also just a lot of our instruments are not really, at least in the US, we're really focused on kind of on attainment of the standard, which is like previously it was 12 micrograms. So they're really trying to be very accurate in kind of the 0 to 20 range, right? And so some of these concentrations are so high that there's going to be uncertainty even in our conventional monitors. So probably more work would be needed to understand what it might be like in the tropics or how to improve performance.
Okay. Next questions. Then I think we will close with questions from Derek and then moving on later on the next Q&A session. So from Wale, in an area where there's no reference sensor, how do you determine the accuracy or positions of the sensor?
Yeah, so that can be very challenging. I think, trying to look at results from areas that are similar to the area that you're in can be really helpful. And otherwise, sometimes there are, instead of setting up a reference monitor, you might be able to collect just a few, filter-based samples or something like that to validate. I think there's some work kind of in development to potentially use other validation methods, models, satellite measurements, those kind of things. So I think that's very much a research topic of interest to the field.
Okay, moving on to the last 2 questions on this session. Does the PMSA 500 tree also give information about the particle number concentration? If yes, you should try to model the PM bin concentration against the PM 2.5 reference monitor. In that case, you will omit the internal algorithm that converts BN into PM.
Yeah, so that's a good question. It also gives you particle number counts, but they're not really accurate based on a number of studies that have been done. And so I would say all the outputs of this device are a little bit like a black box. We're not sure exactly what the company is doing to estimate PM 2.5. We don't know exactly what they're doing to estimate the counts. So to me, those are both kind of black box numbers. And some people have used them successfully to correlate with PM 2.5. But it's kind of just different data.
Okay, next from Derek. Do you have any thoughts on the utility of the API algos versus dynamic corrections coefficients generated more regularly from collocated PA BEM 10 2020s? That's the first question. Maybe you can answer that first.
Yeah, so, all instruments are going to have some kind of bias or uncertainty. So I think in a lot of cases, kind of a daily correction is probably more than you need. It could be helpful if you have a day that's like a very high concentration and very different than your typical experience. Definitely this equation is not going to be the most accurate everywhere. It's kind of like a simple method that does pretty good everywhere, but you could definitely do better with a more tailored correction.
Another question from Derek is that in the Central Valley, the makeup of PM 2.5 changes seasonally, agriculture harvesting and versus wildfire smoke season, and regionally. Any thoughts on how these affects the planetary sensors?
Yeah, so that's a good question. And in some places, I think seasonal correction is really needed. I think a lot of it comes down to the particle sizes. So when you have these PM 2.5, that's more of the larger particles, things like dust that could be from agriculture, instead of smoke, that would be smaller particles. And that is a time where you're going to get more underestimates whenever it's kind of a dusty source from the sensor.
We still have quite time a bit on finishing the questions. Maybe we can just run through all the questions on this session. Next question from Paulo. Hi, what particles are most affected? RH 70 to 90%, for example, fine coal dust, sugarcane smoke, South Africa.
Yeah, so that's a good question. And I think the particles that would grow the most would be particles that are probably more like sulfate and nitrate. So those, it kind of depends on the chemical composition. And so there could be different industrial or transportation sources for some of those chemicals, depending on the local regulations.
Okay, next question from Mohammed. Does the black box element not undermine this kind of corrections work as a change by manufacturers in the background could invalidate current correction?
Yeah, it's definitely a challenge and something to be aware of. And so I think in a lot of cases, when we are talking about sensors, we're kind of talking about two manufacturers, right? We're talking about the manufacturers that are making the internal components, and then we're talking about the manufacturers that are making the whole integrated device. And so I think ideally there would be more communication between everyone, right? But at a minimum, there need to be some kind of checks to see if it's performing, if these new devices are performing similar or if things are changing over time.
Okay, another questions. I think this is the last question from Jim. Some studies have used a collections of sensors co-located to create a proxy reference value. Obviously, this is for sensor variability rather than drift. But could using a sensor intermittently provide a way around sensor drift? Do you have any thoughts on working around the issues of not having access to a reference grade instrument?
Yeah, so the first one, the first question about sensor to sensor variability and using a sensor intermittently, I think that could be an option. If you are in a situation where your sensor is drifting, maybe I think that there isn't, I'm not sure if there's really consensus on what leads to drift. You know, is it just aging of the optics, particles settling, the fan degrading, other kind of issues? So you might be able to kind of leave the sensor turned off for longer and then use it to correct for drift. And in terms of working, I think that somebody else had asked this question about the issue of not having access to a reference grade instrument. And, you know, you're kind of limited to looking at results from other locations that are similar to yours, or maybe trying to use air quality models or satellite data, or maybe kind of a mid-cost option like a couple filter samples or something like that to validate.
Okay, great. Thank you everyone for the questions, and thank you, Karoline, for helping answering all these questions. Looking at the time, we have to move to our second speaker. Our speaker for the second presentation is Siriel. He's a scientist of AirGradient. He's one of our scientists in AirGradient who will discuss the implementation and global performance of the EPA Correction Formula for AirGradient Monitors. A bit of introductions. Siriel's work focuses on processing and analyzing air quality data with a special emphasis on particulate matter. He will provide insight into how AirGradient's global network of monitors is utilizing EPA Correction Formula to enhance the accuracy. So, Siriel, please take your time and start your presentation.
Thank you very much, Johanna. Can you see my slide?
Yes, it's going very well.
Thank you. Thank you, Karoline, for your talk. And moreover, thank you for all your work that you and your colleagues did on this algorithm. It allows other organizations like us to test it and also to use it. It turns out to be helpful. And that's exactly what I'm going to talk about in this presentation, and the question whether the algorithm from EPA can be used for the data from AirGradient or not. And my presentation is based on a blog article that we have published in September. Some of you might be familiar with that. And it is related to a global collocation project that we are involved, where we run this project. This is a picture from Chennai in India, where we have 3 outdoor monitors collocated with a reference instrument. And we do that to understand and improve the accuracy of our PM2.5 reading, also in the context of different locations, different types of aerosols, different seasons throughout the year, and also comparison of different reference instruments, so different types, and also to observe, for example, the drift that might occur as the monitors get older. And this is a project that we can't do by ourselves. So this is a community effort, and we are very happy and very grateful to have all these organizations that help us with collocation. And it's a big thank you to everyone who is involved in that. And without you, it would not be possible. So for this analysis that I'm presenting, we have looked into 9 locations on 4 different continents, Africa, Asia, Europe, and North America. And in total, we have more than 6,000 daily data points for PM2.5, where we have collocated reference data available. And that's all these locations, that outdoor open air monitors from AirGradient. And this is just like 2 plots as a first result. On the left, we see a plot with data from Switzerland. On the right, we see data from India, Chennai. A total of 50 days, I think, for each of the 2 plots. And in red, we see the reference data, and in blue, we see the air gradient. And if you watch carefully, you can see multiple blue lines. That's because we have multiple open air monitors at the same location. So this plot doesn't only allow us to compare between AirGradient and the reference. We can also look at the variation within the AirGradient monitors themselves. And something that we observe here in these 2 plots is that the raw data from AirGradient tends to be overestimated, especially at higher concentration. So as the concentration goes down, we see that the reference data and the AirGradient data, they match better. And in some cases, we see that at low concentrations, AirGradient underestimates the PM2.5 concentration. We have observed that for all 9 locations, not just these 2. So this seems to be something systematic. And we are now wondering what happens if we correct this data with the algorithm that has been introduced by Karoline. This is now an example with data from Cambridge in England. And on the left, we have a time plot with the raw data. And on the right, it is corrected with the algorithm. And we see that when applying the PM2.5 correction algorithm, in general, the PM2.5 readings, they get lower, and it gets closer to the reference, at least in this example in England. And it's not just here in England. Actually, we have seen that in in all locations, 9 out of 9. I'm not showing you all the plots now, but I will show you a summary of all the data. This is now a scatter plot, or 2 of them. On the left, it's with the raw data, and on the right, it's corrected. On the x-axis, we have the low-cost data, the AirGradient data, and on the y-axis, we have the reference. And ideally, we would observe that we measure the same concentration with AirGradient as the reference does. In this case, we should see a perfect line, 1-to-1 line, which is here the red line. But in reality, we do not see that. So as already mentioned before, we see that in general, the low-cost data from AirGradient is overestimated. That's why they appear below the 1-1 line. And if we do the correction here on the right side, we see that these data points, they get closer to the 1-1 line. It looks like that not all locations behave the same. We have different colors here for different locations. If we look at the dark blue color, which is Vanderbilt Park in South Africa, it looks like that the correction algorithm does not work as good as it does for the other locations. We have looked into that, but so far we have not figured out why. Could be that the aerosol is different at this location. But it could also be related to the reference instrument. That's something we keep investigating. So this way of looking at the data, it doesn't give us numbers. It's just a visual way to look at the data. So if we look at numbers, then we can look at a table like this, and it gives us the R-squared value, for example, for the raw and the corrected data. That's the correlation coefficient. And it also gives us the normalized root mean squared error, for example, which is the error of the sensors for all different locations. And in general, the bigger the RMSE, then the less accurate the sensor. So we want this number to be low. And if we apply correction, then for example, here in N-Accord, we have a raw NRMSE of 87%, and with correction, we bring it down to 34%. That's quite a significant improvement using NRMSE as a metric. So in this case, we have an improvement factor of 2.6. And if we do that for all the locations, we see that in all locations, we have a positive improvement factor. So we can say that using NRMSE as a metric and daily data, we observe improved accuracies in all locations when we apply the correction algorithm. And on average, it's an improvement of 2.5, which is quite significant. But we also see a variation. For example, in London, Marylebone Road, the improvement factor is 1.4, which is still significant, but it's lower than, for example, in Dübendorf, in Switzerland, 3.8. So there are differences between different locations. So what does it mean? It means that we, in the team of AirGradient, we decided to implement the algorithm from EPA for 3 reasons. First, in all investigated locations, 9 out of 9, we have observed improved accuracy when correcting data. Then second reason, we like harmonization, and the algorithm is already established. It's used by Purple Air, it's used by the EPA Fire and Smoke Map, so we believe it makes sense if we use the same algorithm to allow better comparability. And then the last reason, this model has not been developed with our AirGradient data, so there's no training bias from our side. When implementing an algorithm, it can be risky because it may introduce confusion. So we have on our website, we have a page where we clarify which data is raw, which is corrected. And as a summary, I can say that the dashboard data, so the plots and the tables, they are either raw or corrected. It depends on the setting. The users can select what they want in the advanced settings. And on the other side, when users download data, so either on the dashboard or through the API, the data will be raw, and users can apply correction manually if they want. And on our map, the data is either raw or corrected. This again can be selected by the user with a little drop down. Then last slide, we have not implemented the algorithm exactly as stated by EPA. We have done 2 modifications. First, we have 0 as the lowest output. So we observed that the algorithm at low concentrations and high humidities, it can lead to negative PM2.5 values with a maximum of minus 2.9 microgram per cubic meter. And we have defined that 0 is the lowest output. And then the second one, if the raw reading is 0, then we interpret this in a way that the reading is below the limit of detection. And in this case, we do not apply correction. So the reading of 0 remains 0. But if the reading is, for example, 0.1 microgram, then it will be corrected using the algorithm. That's my last slide. Thank you for your attention, and I'm happy to answer any questions if there are some.
Thank you, Siriel, for the presentation. I think we can right away start with the Q&A sessions. Now we have one question from Derek. For raw data from the sensor, are you returning from CF1 or CF-ATM?
Actually, Achim might be better to answer this question.
Yeah, at the moment, actually, we're upgrading the firmware to deliver both. I think it's the atmospheric, if I'm not mistaken, but I get back to you, Derek, exactly on this.
I think the same, yeah. I think it's the same channel as Karoline.
Thank you. Another question is from Ohad. 2 questions. First, can there be 0 particle, I believe? I'm not sure about this. Is in the background always something? And then the second question is, the correlation drops for higher concentration. She thought this might stem from the conversation from counts to volume, specifically the use of a ball volume equations, which is dependent on diameter to the power of 3. Very not linear.
So for the first question, I think yes, there is always a background. I think it's really hard to get a 0 microgram per cubic meter air. There are some people that try really hard, like for pharmaceutical applications or semiconductor industry. But normally there is always something in the background. But we observed that in some cases, the plant tower sensors, they indeed report 0, like 0.000. And we just believe that's below the limit of detection then. It doesn't mean that the actual concentration is 0. And for the second question, why does the sensor overestimate at high concentration? That's something we thought about a lot, and we don't have the answer. Personally, I believe it's related to the conversion from the optical diameter into the aerodynamic diameter. We need to understand that this sensor uses light scattering to measure particle concentration and also particle size. So this means it measures the optical particle size, but PM2.5 in general is defined as aerodynamic size. That's a different concept. So I think Plant Tower as a company, they convert optical diameter into the aerodynamic diameter using simple math. There are some equations, but it needs density as an input. It needs refractive index as an input and shape factor. And usually these things are not known because the aerosol is changing all the time. So I think they just make an assumption for a density, for example. And maybe the assumptions that they make on average lead to overestimated numbers. But this is speculation.
Thank you, Siriel. We still have time for the Q&A sessions. If any of you want to ask questions regarding this presentation, please feel free to drop in the chat box, or you can ask directly from the mic. Okay, we have another questions from Stefania, which I think it's either for Karoline or for Siriel. Okay, so the question is, could the algorithm be applied to indoor low-cost sensor as well?
Maybe I can answer that because we've looked into that. I think also have some slides actually. So our collocation project is not focused on indoor sensors, but we also have one collocation where we have indoor monitors. So that's the AirGradient 1, which is collocated with a reference in Manchester in England. But the reference that is in place here is not an FEM and not an FRM. It's a bit more sophisticated sensor that we use, and it's also considered to be equivalent to an FEM, but it's not official. It's not certified. And based on what we have seen in this collocation, we basically see the same as with the outdoor, so that we overestimate indoor and to a similar extent as outdoor. And when we apply correction on the right side here, we pretty much get a good match with the reference data compared to the raw data on the left. And to me, that's not surprising because the indoor and outdoor monitors from AirGradient, they both rely on the same sensor technology. It's the optical sensors from Purple Air, from Tower, which also is used by Purple Air. So to me, it makes a lot of sense that we see similar behavior between these different monitors because they use the same sensors from Tower.
Thank you, Siriel, for the answer. Next is a question from Anika to Karoline. What do you think about the machine learning supported correction as compared to formulas that are based on physics?
Yeah, so that's a good question. And I think that usually machine learning is more complicated than you need to go with sensor correction, because I think the more complicated of correction that you use, the more important it is to, when you're developing the correction, to experience the full range of all the different parameters that you're including in your model, right? So not just a full range of PM and relative humidity, but a full range of all the conditions too. Otherwise, you can get, unreliable results when you start extrapolating. And obviously, you can get unreliable results when you extrapolate any model. But if it's less complicated, then you're going to be less likely to be outside of the range or far outside the range of what it was trained on. So I think machine learning may be needed for some of the gas sensors that have more complicated dependencies. But from what I've seen, a lot of the PM sensors, you can do okay with physics-based or, multilinear regression type equations.
Thank you so much, Karoline, for the answer. Great. Looking at the time, it looks like our time is almost up. So to wrap this up, I'd like to thank Siriel and Karoline for the great presentation. I see that a lot of enthusiasm from all of the attendees. There's a lot of questions going in. For the rest of you that we might not answer the questions yet during the Q&A session, don't worry. We'll list everything and then we'll reach out back to you after the webinar with the answers. Thank you so much, everyone. Thank you, Siriel and Karoline. Looking back, it was a very interesting discussion. And for those of you who's interested for the recordings and materials, don't worry, we'll publish everything on our website by next week. So stay tuned on our LinkedIn for the information on whether we have published it or not. Thank you so much, everybody, for joining in. Have a good rest of the day. Thank you.